Okay, so now you can get an idea of how it works. You can post a picture, you can write a comment, you can like the other people's comments if you like their comment, you clearly like this one. And if someone writes something that's worth discussing, we can start the discussion too. Okay, some more things popping up now. I'm going to give you like another 30 seconds before I start asking people about these questions. Maybe not the AI one though. Okay, maybe we can start discussing some of these things. So someone said how to improve the current detection, any more analysis that we can do. So anybody want to kick that off? I know that, you know, we use CWB at the moment. Sergey has a comment. You can do that side and I'll do this side.
Yeah, this is what I'm going to talk on Friday. Actually, also the second question, what SNR needed for SNR supernova detection, but it's much easier question to answer. As usual, SNR 7 or larger, right? But the problem is, what SNR do you have in mind? Is it match filter SNR as usually we calculated, or detectable SNR? And depending on the type of the signal, like this beautiful signals which we see all the time, I would say that you need at least SNR of 15 match filter to detect something. Yeah. And for reference, for example, if you're talking about binary black holes, that it's SNR 7, 8, it's already detectable. But there is a good reason, why this is happening. But again, I will discuss this in my talk. I don't know if we can talk now.
Yeah, I'd like to talk about that now. So, okay, you can go that way. Yeah, so we know that we can see binary black holes down to like signal to noise ratio 8, but for supernovae, we're only going down to much higher frequency signal to noise ratio.
I actually asked this question, and the reason is that I looking at the paper, I have the impression that the more complex are the more. I mean, whenever you take a signal, you're making the analysis of signal, which is, I don't know, 400 milliseconds, so the simulation stopped and you are just injecting that. You are getting something like 15, but when you get simulations that are more complex, that are longer, then it starts increasing. So I don't know if it's my impression or if there is some systematic study about that. So the more realistic is the waveform, is larger the SNR, or it's just my impression?
I think that is what's happening.
Are you implying that like a longer signal might be harder to detect? Is that what you're?
Yes.
Yeah. So I'm speaking on behalf of Bayeswave. I don't know how like CWB or other algorithms work, but like technically we can better reconstruct signals that are more compact in time frequency. And that's because in Bayeswave, we place wavelets in the frequency domain. And like, we want them like, so let's say if you have a 15 SNR signal and it goes for 2 seconds, at each time frequency pixel is like your energy is divided across 2 seconds instead of like, and if you have another signal that's 0.5 seconds, let's say, your SNR is more compact in that area. So which means your wavelet placement's more confident because you have more SNR like clustered in that one area. So the longer your signal, and if it's 2 signals with 15 SNR, one's 2 seconds, 1.5 seconds, the 0.5 seconds will be detected a bit better. But
I know how to answer this question. Imagine that you are standing on the gravel road, okay? And then you see a big boulder, which is it's a boulder which is relatively small, right? And then you can spot it on the gravel road pretty well. It's not blended in. And this growl, it's a noise, detector noise. Now you split this boulder into small pieces and redistribute uniformly on the ground. Will you see it? Probably not, because these small pieces, they will blend into the noise, and this is why supernova signal is very hard to detect. And unless you know that, let's say that the growl rod is black and your boulder was white, then you can pick up all the stuff, and this is called a match filter.
Yeah, sure. So yeah, so it may be even more difficult than 15. It may be, in many cases, in a realistic case, it could be 25 or that's my worry a bit. That when you go to a realistic case, maybe it's 25, which puts a stronger constraint on the distance. And yeah.
Yeah, but we can do something about that. So if you have two detectors, so it means one rod, another rod next to it, and then we have black noise, and then white pebbles scattered in both detectors. And now if you can correlate these two pictures, we can extract the signal much more efficiently.
Okay, so in this case, which SNR, do you still, in this case is where you get 15 or?
Because no, in this case, you can detect a low SNR event.
Okay.
But still not as good as a match filter, but pretty close to it.
Okay.
But the problem with this kind of approach is that computationally it's almost impossible. Yeah, that's why, actually there is algorithm which actually can do that, but probably it's not optimal still.
Okay. Thank you.
And I'll talk about this.
Yes.
Yeah.
So actually, I just wanted to ask, when people talk about detection, like what does it mean? It's like, so SNR doesn't really say anything unless we have a false alarm rate kind of estimation, right? Because it depends on the PSD, depends on how noisy that chunk of data is. So I've seen like people setting different boundaries, like like false alarm rate of 100, like 1 per 100 years, or like 1 per 10 years. Like, what is the? I guess I know there's no correct answer to this, but like, kind of what is the widely agreed on number? Do we have one, or do we want to discuss that? So that might be.
Yeah, I'm going a bit provocative. I don't think we need the 5 sigma criteria for discovery, because for a core collapse supernova, we should have the neutrino information. If we have the neutrino signal, we know there is a supernova. So the point is not to make a discovery. We already know there is an event. It's to estimate how significant the event or the gravitational wave signal is. And we will give a number. We'll say we can measure, we will reconstruct the SNR. But I think the most important thing is the nature of the different features we can extract from the data. And that's more than the number of sigma. We don't care. The neutrino will tell us there is a signal.
Jade, I have a quick question. Is there a way we can, after have a page with all these questions with the answers that come up? Because I think that's going to be interesting to keep track of some of the answers.
Yeah, we can definitely keep the page. I will just make sure that I don't close it so that I don't lose it until I've recorded it somewhere. Anyone want to go next? Shall I go back to the questions? Yeah, go for it.
Can we measure polarization? The answer is no. With 2 detectors which we have right now, it's impossible. You mean point in the sky?
Yeah, like if the objects flew up.
Yeah. So essentially, the place, we all can kind of visualize antenna patterns. There are 2 sensitive spots, then somewhere like in between, and then 4 totally insensitive spots, right? You can measure polarization. but only in this insensitive spot where the detector sensitivity like more than order of magnitude lower than in the sensitive spot. So it means that the supernova should be really close for current detectors. For detectors like Cosmic Explorer and Stein telescope, it's a different story because Stein telescope has 3 detectors in it. And then there is a hope that we can measure polarization. Yeah, this is also what I'll discuss quickly.
Anyone else want to say something about polarization? No. Okay.
So I'll speak to the question. There's a column of questions. First one from Quirky Duck. Modulo what Sergey said, I was going to say, what can we learn from Betelgeuse? Everything. I mean, yeah. So, I mean, we'll have a very, very detailed neutrino signal, gravitational wave signal. We'll have information across the electromagnetic spectrum. It's a galactic supernova. It's not that far away. It will be, you know, if only Betelgeuse will cooperate with us, you know, it'll be the event of a lifetime. I'd like to address the question, if you could scroll back up a little bit I'll refer to you as AT, Adorable Trout. Both questions, the one below as well. So what is the minimum temporal separation between prompt convection and beginning of high frequency feature? I don't know that that can be answered in a precise way, but what we can say, and others here can chime in, prompt convection develops on the order of 10 milliseconds. And of course it develops and then it wipes itself out. But as Sophia pointed out in her poster Sparkler, its impact can last longer than that. So order 10 milliseconds, we're talking about the development of prompt convection. The high frequency feature requires the development of other convective instabilities, the neutrino-driven convection and its accretion onto the protoneutron star, as well as sustained Ledoux convection, which is sustained long-term. Both of those develop on the order of 100 milliseconds. So we can speak to the rough timescales for the development of those things, one being prompt early and the other being later. But with prompt convection, you know, again, it's going to continue for some period and its impact will continue for some period. And, you know, there may be overlap between the two epochs. And talking about a minimal temporal time between that, one would have to look at the data on a case-by-case, the detailed data from the models on a case-by-case basis to speak to that. And then what is the minimal temporal separation between the beginning of the high frequency feature and the beginning of the SASE? Those again are going to be order 100 millisecond timescales. They're going to be almost coincident in the start time, and it may be difficult to pin down any temporal difference. It would be small probably, and again, it would have to be done on a case-by-case basis. So I hope that helps.
This is one comment. When I comment to a question that was asked about the SNR. By the way, this is Adorable Trout, and no, I have a suggested question that we didn't touch today about the minimum SNR for the detection. And one thing that I think might be useful is to break the question in two parts, because someone could say, what is the minimum SNR for 2 sigma, the minimum SNR for 3 sigma? And the answer is different. But one interesting question is, what is the minimum SNR that our algorithm will reconstruct an event at all? And that's because if it doesn't reconstruct the event at all, you cannot even try to debate. So I think both, one depends on the opinion of the community to declare detection. The second one is a hardcore threshold of the algorithm, and usually 5 or 6. And I think it would be useful to know for base wave or coherent wave burst, what is this hardcore threshold?
Anyone want to respond?
If it's bar instability, then it's detectable, at SNR of 7. And if this is like C15, then the best probably what we can hope is SNR of 15 or a little bit lower than that. I mean, much filtered SNR. Because when it's
it is spread out.
when it's below SNR 15, it starts to blend into the noise completely. Even kind of to detector correlation is not helping in this case.
I guess I can answer the question about what's on slide 17 of my presentation. That would be the power gap, I think, which is a very mysterious and weird thing that is seen in many modern simulations. And it's strange because there's this narrow band of no emission. I think it's a real thing, at least in terms of that it is there in the simulations, and it doesn't really depend on how you do the Fourier analysis and stuff like that. If you know what it is or have any ideas, feel free to send me an email, because I know how little I know about it. Let's say it's mysterious and it's weird, and but it's interesting, and I don't think it is an avoided crossing.
That was going to be my answer. I'm pretty sure it's an avoided crossing because it always appears there when you do the analysis. But yeah,
We can argue.
maybe yeah.
So I was just kind of like thinking of an answer to Michele's question about how to define like a hardcore threshold for different algorithms. So for Bayes wave, I think there are like kind of 2 detection conditions. So first of all, because we use Bayes factor between different models as our like kind of detection statistics, right? So we've got the signal model versus the glitch model. The signal is like a coherent signal, glitch is an incoherent signal. And then we've got the Gaussian noise model. So the first detection condition is we have to make sure that the the Bayes factor between the signal and the Gaussian noise model is more than 0. So the log Bayes factor is more than 0, which means we're more likely that we're more confident that this is a non-Gaussian feature than a Gaussian feature. So that's detection condition number 1. So once we've made sure that it is more consistent with a signal, then we have to make sure it's more consistent with a glitch, which the log signal to glitch Bayes factor comes in. Because even if we have a positive signal to glitch Bayes factor, but then we have a negative signal to noise Bayes factor, then the whole that signal to glitch Bayes factor doesn't mean anything, because we're comparing like 2 non-Gaussian models for a Gaussian event. So that's detection condition number 1. And number 2 is the log Bayes factor, but then that comes down to the false alarm rate, because the Bayes factor, like some people go like if you have a Bayes factor more than 3, or as an arbitrary number as well, then we have a confident detection. I personally don't trust that, because I run Bayes wave many times on different data sets, and every data set has a unique background. So which means we can't actually set a hard Bayes factor, saying Bayes factor 10 or something like that will give us a confident detection. So I think ultimately the FAR method is probably the best way to determine a confident detection. So again, it comes back to the question of what FAR do we want to accept as a community. So that's kind of the answer I can give you. Yeah, thanks.
I like the question about stars in our galaxy that might blow up, and how well do we have them catalogued, and especially would we notice if one disappeared, because that would be a good gravitational wave candidate. So I don't know if somebody who knows about observations of stars in our galaxy wants to comment.
Chris, where are you?
Yeah, Chris, you want to? You know
But
about
before
stars?
Chris talks and can prove me wrong, one thing, if it's within our galaxy under 10 kiloparsecs, we do have one list, and it's Betelgeuse. But beyond that, there has been some work in the neutrino detection community looking at pre-collapse neutrino signatures from nearby stars, where we might see something on the order of a couple days to a couple hours, maybe, depending on how close it is. But Chris will probably completely prove me wrong.
Wait, so I missed it. What was your comment for?
Betelgeuse.
Yeah.
And then some of the neutrino detection community has been looking at pre-collapse neutrino emissions, so during the late stages of burning. But that have to be very close, closer than 10 kiloparsecs would be my guess.
Yeah, so I don't know does someone who's done, I mean, you get some neutrinos, but they're not that strong. I know I've seen papers on this, but I don't know what the answer is, how close they have to be detected. We should look to see what something like Hyper K could do for that. Something that is interesting here is, and data, and maybe Marco knows the answer to what the neutrino fluxes are. The other thing that we will have with a galactic supernova, with something like COSY, is really detailed yields from. So the problem with getting yields from any kind of atomic spectroscopy is you have atomic physics. If you're doing instead radioactive elements, the uncertainties are much smaller. And so one of the things that we'll get with the galactic supernova is the detailed yields from all the radioactive isotopes. And that tells us things that those are produced both in the shells and in the engine. So that would be a really nice constraint. So something like COSY would really give us a lot of data on exactly what's going on in these, if what's the electron fraction, that's going to be pinned down by the detailed yields from these radioactive isotopes that, I mean, COSY's looking at how can it deal all the way to the Virgo cluster. In the galaxy, it's going to get detailed signals.
Tony?
Since we are most confident about detecting core collapse supernovae less than 10 kiloparsecs away, do we have a red flag list for the stars to watch the hardest in case they go supernova? How far out have we confidently cataloged most likely core collapse supernova progenitor candidates?
We must have that list. I don't know where it is, right? I mean, we have actually listed, yeah. So but I don't know. I don't even know who I would go talk to. But
Yeah.
But we must have that list.
Sorry, Olivia, I tried.
Yeah, what I want to know is if they're remaking the list, like is one missing that wasn't there before? Because that would be a good candidate for a gravitational wave search, right?
Okay. There's a team. So there are the people, the team that Chris Kachanik's team must have a good list, because they've been staring at things, waiting for the stars to disappear, right? And so they're looking for black hole formation. I would go look at their list, because their list must be pretty complete. Yeah.
Assassin is the collaboration.
If you Google assassin, God knows which. Yeah, it'll be a list you don't want to see.
If I may add a comment to Betelgeuse, as far as I know, there are observations of pulsation of these stars that tell us that this star is still far from the explosion. So still it's 10 to the 4 years before the explosion. So there is no way for us, I think.
Oh, did you? Yeah.
I just have another comment. I think there's also one recent paper saying that Betelgeuse has found is a companion star. So it's actually is in a binary system. So it's probably the evolution state will be. Huh? Yeah. Yeah, it's a.
But you've seen something more recent. Okay.
Okay, thank you.
I think you scrolled up. You covered part of the question I was going to start. I want to go up above gentle quokka. Yeah, right there, valiant tiger. Actually, I think there's one above that. Yeah, loyal otter, right? I don't want to know who loyal otter is. So being realistic, what are the concrete directions on the theory and detection sides to prepare the ground for a core collapse supernova gravitational wave signal? So I've been asked to talk about the next 10 years on Friday, together with Marianne on the detection side, I on the theory side. So I will address this in much more detail. But I did want to say a couple of things. So first and foremost, I think the concrete directions, I mean, I think you're looking at whoever Loyal Otter is. I think what we're doing here is one of the most important things that we could continue doing going forward. Obviously here, we have the benefit of having everyone with differing opinions on both sides of the fence together to discuss this. But certainly collaborations between the modelers and the detection folks, shoulder to shoulder, hard work, day in, day out, is critical. And obviously gatherings like this, repeated gatherings like this will be absolutely critical. One other thing I'll add is what has helped me is to understand from the detection community, what can be seen and what cannot be seen, what is useful and differentiable and what is not. So that has helped us to understand how to prepare and present our data to the detection community. I'll let somebody on the detection side speak to what has helped them thus far. But just sort of two initial answers to this wonderful, wonderful question. And we'll talk more about this during the week. And then Marianne and I will be looking very much in the future on doing precisely this.
Somebody asked at the bottom if LIGO was on in 2014 because there was recently a paper about a disappearing red supergiant, and no, it was not on in 2014, unfortunately. Anyone want to take a shot some more?
There was a question how we would detect a failed supernova. And I think that one goes in some regard in the category, how did we declare a detection of the binary black hole merger, the first one, because we didn't have an electromagnetic neutrino counterpart there. And so the question is that, for that scenario, Marianne, would you still up for going below 5 sigma if we don't have a neutrino electromagnetic counterpart?
Of course, that changes scenario, but in that case, for the first BBH, of course, it was a 5 sigma in terms of force alarm rate. It was a 5 sigma detection, but the shape of the signal was also a convincing argument. And of course, there's been lots of discussion if it was really a BBH, a compact object, and blah, blah, blah. But the shape of the signal was really an argument. So for core collapse supernova, I think what would be very important is to get the feature of what we expect from a core collapse supernova. G mode, core bounds, convection, and so on. So the data themselves will bring something. Will bring some information. And of course, if we see a weird signal, we're in trouble. That's clear. If we have no neutrino, we have something we don't, we see just white noise. We don't see anything, no bounce, no modes, high frequency modes, only white noise. Yeah, we are in big trouble. That's for sure. And no neutrino, no electromagnetic counterpart. Yes, that's the worst case scenario, of course. And then we are back to the problem of what it is and 5 sigma detection. I think 5 sigma detection will not be enough.
Yeah, I just wanted to mention that if you have a failed supernova, you still have a strong neutrino signal. It's actually almost the same sigma as a regular supernova explosion. So it will be very visible and evident for everybody that there was a failed supernova. So just to clarify, I mean, if you see something that it looks gravitational waves like a supernova, but there is no neutrino signal in the galaxy and no electromagnetic signal in the galaxy, then probably it's not a supernova or a failed supernova. So a failed supernova has a strong neutrino signal.
I think we're also missing part of the signal, right, in that situation, because our simulation codes go up to right before black hole formation and then they crash. So we don't actually have the gravitational wave signal for the neutron star collapse to the black hole, and I guess you'll have a little ring down, but I expect that part of the gravitational wave signal will probably also be very loud.
Oops.
Change in the future, right? It basically, you need singularity avoidance. So the numerical relativity community has developed this over many decades, and now that is working its way onto the supernova side. And so if you have that, then you can develop the entire observable space-time, depending on the slicing. I mean, if you have slicing where most of your grid points are sucked down the black hole, then it's a problem from a practical perspective. But if not, then you can develop the space-time, the observable space-time, and the code shouldn't crash, except for if it is a problem, another problem.
I have a question related to the failed supernova for the theorist, and what I know it's made of 2 parts. The first part is the duration of the SASI. It is my understanding that if someone has a SASI that start becoming too long, it's a strong indication that most likely the supernova will fail. I know that Thomas at certain point was commenting that, but he was also commenting that you can make a model of the SASI last as long as you want. So I don't know if after 9 hours after that comment, you have a different way to phrase it. But related to that is now, as time passes, the noise will be such that we can reconstruct the high frequency feature higher and higher. And now we probably go about 2000 hertz. Is there an opinion that you cannot go for the above a certain frequency, and because it's going to collapse into a black hole? So I don't know if any of these 2 questions you have a comment, or anybody else.
I don't know exactly what statement of mine you quoted, but of course, if you had a continuing accretion of a neutron star, which in the end doesn't achieve an explosion, to trigger an explosion, you have the chance to obtain a long-lasting SASI episode. We had such simulations over maybe a second or so. There's not a large set of failed models because the Fornax simulations explode nearly everything they try. In our case, we don't have the computer time to run dozens of models in 3D until we achieve the black hole limit. But I would say in principle, this possibility exists. And in that case, you accrete on a neutron star, which gets more and more mass. It's heavier and heavier. And then you would expect this G mode frequency to ramp up to maybe more than 3000 hertz. Yeah. So that in combination, on the one hand, the shaking SASI, making the neutron star vibrate, and then this extra component coming at high frequency that would come together. Yeah, that possibility exists. How likely it is, what are the chances that the next core collapse in the galaxy has such a signal? I would say at the moment, from the theory side, we can tell. Probably very unlikely what Fornax concerns, relatively likely when we take our Garching simulations.
I would perhaps nuance that a little bit, Thomas, because the thing is, of course, as long as you're considering the fundamental modes or the low mode nodes with few radial nodes, the frequencies are limited by things like the sound crossing time in the neutron star, and your neutron star before collapse will not get arbitrarily compact. So there may be something like a cutoff for things like the high frequency signal, but you could.
Because this was seen in some.
In some, yes, yeah. Yeah, but I think it's a good question. How far can you go up? I think there might be a limit. The other thing is.
This was Michel's question, but.
Yeah,
maybe. So we studied systematically different wafers from different people to see what was the span, because we were interested in the range of values that are possible. And I have it in front of me, and the maximum values that you get is about almost 3000. I think there were some simulations of PAN, which a very compact progenitor and a very, some equation state that was favoring high mass. So 3000 should be reasonable.
Yeah, just following up a little bit on this discussion, I'm kind of wondering maybe the other way around. Are there any smoking gun parts of the signal where we can say, okay, we can really think it's scenario A, B, or C, right? I hear a lot of features and processes. And what I'm thinking is, okay, but those could exist in model A and B. Have we really thought about, if we want to make the bridge to observation, how do we know when, what happened, if it happened, and then also, what actually happened?
Anyone want to take a shot, or shall I try?
Let me ask back. Connie wants to answer. Is your question, when consider the case you had a signal which would be the smoking gun features which would clearly indicate a particularly distinctive scenarios? Is that the question you wanted to answer?
Right. For example, failed, not failed, right? I'm just giving an example.
Now, an example, if you had a long-lasting, very long-lasting SASI episode suddenly stopping, then you probably would think of a black hole collapse, because it's very unlikely that you get a very late explosion. That is one of the issues which one might be able to relatively easily diagnose. Yeah, maybe other features, of course, which could be indicative of a successful case. Not sure that this G mode contribution, if it fades at some point, maybe the instigation by downflows ends, and then you see that the explosion has been successful. Not so sure that there is any, in the other way around, that there is any absolutely 100% clear signatures of a certain dynamical event going on.
Yeah.
But the black hole collapse situation may be identified clearly. Yeah.
So maybe just a follow-up, and
Yeah.
that maybe goes more towards people who do the analysis. To what extent can those features be identified as that, right? Are there other processes, not even supernovae, or even glitches or things that could really throw you off and give you the wrong conclusion? So I'm even trying to say, in a burst landscape, are there other similar, astrophysical processes that could give, signals in that frequency regime with that length?
So I've never seen anything gravitational wave signal or detector noise that looks like the high frequency GRF mode. Like I don't know any other thing that would make that other than a supernovae. But if you have a case where the signal to noise ratio is pretty low and you only see one small blob of the signal, then I think it would be much more difficult. Like if you could just see one little blob of the high frequency mode, so it would just be a high frequency blob. Or if you get, you know, like if the prompt convection was louder than the rest of the signal, then you'd just get a few spikes at like 60 hertz and it would look like an intermediate mass black hole and everyone would say it was that. So I think if you see the whole, if you see the modes, it would like, I would be sure it was a supernova because nothing else looks like that. And but if you only see a small part of the signal, I think you have a much harder time proving that it's from a supernova.
I think Tony has a response to Chion.
I just wanted to follow up on Thomas's comment with which I agree. So for example, if you have feature or the high frequency feature first, so if you have initially emission and black hole formation at that time, then as Tomas said, you know, that will go away. But also on a longer time scale, as we have shown, you know, you go from accretion induced to internal Ledoux convection induced gravitational, high frequency gravitational wave emission. That will also go away. The other aspect of it too is the memory, right? So certainly the memory will have, if it's a failed supernova, then you know, if you look at the neutrinos will be there, right, and will contribute to the memory and maybe even dominate the memory. But clearly, if a black hole forms and you have a sudden truncation of the neutrino emission that's generating that memory, you're going, you know, we're going to see something fundamentally different in the memory signature as well. So what we need, of course, are more models that go, as Tomas said, is very hard, you know, in you know, the state-of-the-art models, it's very hard to explore multiple seconds. In fact, it's quite impossible. If you're exploring multiple seconds, then you're making approximations to be able to do that. That's just a fact. Flops are flops, right? So we need more models, particularly, you know, models that are, you know, as best as we can produce without cutting any corners, and to evolve over multiple seconds to really be able to see what these changes look like. But Tomas is right, and I would add that there are additional aspects to that. So I think would, you know, we would be able to tell the difference in the galactic case, particularly with additional future models that can push to longer timescales. But it's going to take time to get there. And the computer resources will have to get better for the models that are state of the art to be able to run, you know, for 5-6 seconds. I mean, just to give you an example, the Oak Ridge team, UT Oak Ridge team, we can run with an entire year's allocation, which is one of the largest on the Oak Ridge Leadership Computing Facility, which is the biggest, fastest machine in the world, about 3 supernova second equivalents, maybe a little bit more at this point. So that means we can run 3 models for 1 second or 1 model for 3 seconds. That's not a great choice, right? And so, you know, that gives you a sense of what's going to be required to be able to generate many models over multiple seconds. You know, we have that today, and that's all good, but we have that because there have been approximations made to make that happen. But eventually we have to get rid of that and continue to push out.
Yes. So I just wanted to echo an earlier point that models that fail to explode or explode later would have higher neutrino signatures because they simply continue to accrete for longer. And models that fail to explode, which are pretty uniform across most groups, tend to land at 12 to 15 solar mass range. How robust that is likely a function of the progenitor properties we inherit. But I also want to distinguish between black holes. Not all black holes are failed explosions. And so if you have a black hole that's formed from a successful explosion, you would still have ejecta. And so you could still have a matter memory contribution. And so if you see cessation of the SASE signature and any high frequency signatures and the neutrino memory, but you still see continued matter memory at tens of hertz, that could indicate that you've seen a black hole with a coincident explosion. Hopefully you'd have ENM follow-up there too. And then an earlier point was, what can we do? I think this is raised yesterday too. The best thing to do is to make the data public. Many of us, I have the data public on my website. Anyone can go and find neutrino data, gravitational wave data there. I'm sure other groups do too. There should perhaps be a more concerted effort to do this with intention. And then finally, and I want to advocate back to Janka, Tomas about this, what can you do for 1987A? I think your group is the only group that has modeled the 87A. I don't know if there are gravitational waves there. This was a blue supergiant, maybe from some sort of storm merger event, so it's hard to find models for this that are publicly available, readily available. I would guess yes, we can see gravitational waves from an 87A-like event. We've seen this, many groups have seen this, that any model that goes off from 8 to 60 solar masses would have a visible signature if it were galactic for LIGO, and even more visible for future generation detectors. I can't imagine that A7A would be distinct enough for us to not see its gravitational wave signature.
So I just have something to add to part of what you said, which is, when you make a black hole, there is ones where you can have a weak explosion and still have ejecta. But even if it doesn't, eject anything, it's just one of these collapsing to a black hole. At some point, you're getting an accretion, and you expect to have X-rays. So I mean, we should be thinking about the multi-messenger to these different scenarios, because I think, you see something where you see a signal that fails, we need to get the X-ray telescopes on that almost right away to see what else do we learn from it, because I think we can add some information if we do the multi-messenger observations.
There was an interesting question before whether there were similar signals from other sources. I think this question is not answered. I mean, what you see in these G-mode things is just a neutron star which was hit hard. So if you had a neutron star with planets and the planet crashes onto a neutron star surface, I wonder what would happen. If you had a situation where maybe a neutron star, I don't know whether this is finally settled, a crack in the mantle or in the surface may also be instigated to do internal vibrations. So I don't know whether people can really set serious limits to such possibilities, and whether we know whether these sources could. There has been a recent suggestion of a super outburst where a reconnection event in the magnetosphere hits the neutron star surface and ejects matter. So that would also be an energy release of the order. These people took 10 to the 49 ergs of a reconnection event hitting the neutron star. So that will also make a neutron star vibrate, and these superbursts are not as rare as one might think. So there may be other sources out there which could be potentially detected with such a high frequency signature.
So at least the magnetar waveforms that we have access to, they decrease in frequency with time.
Oh, this was a question that went back to earlier in the discussion when you were talking about simulating the collapse of a neutron star into a black hole and how all the simulations break because of the singularity point. But if the black hole were modeled as a Kerr black hole, wouldn't the singularity be like a 1D ring, and would that cause it not to crash, or would it being one dimension be undefined in 2 other dimensions or 3 other dimensions? Would that still cause it to crash?
We have an answer over here.
I think all of these things can be overcome. If you really have there are situations where you have accretion onto a more or less stationary black hole, where you could certainly get any kind of, with the methodologies that are available, any kind of signatures, including gravitational wave signatures. As Tony said, even for the collapse case, it's not unsurmountable. It's just a problem of having the relevant numerical relativity treatment in place, and also being able to evolve perturbations in space-time that may be relatively weak and can easily be spoiled by numerical noise. But it's not a problem that can't be overcome technically, and it will be overcome.
I have a question for Chris or someone with comparable knowledge. I don't know if Chris Fries you're gonna include in your slides, and this is part of one of the questions I raised this morning. Is there any understanding what is going to be the time scale after an explosion where specific useful electromagnetic signature will become available? So for example, if we have a rotating progenitor, how long is going to be before we can measure Doppler shift to titanium line? Or if we have a first supernova, what are typical or possible time scale for an X-ray emission that is detectable in the galaxy? Are there studies that have quantified possibilities of these kind of things, or?
Yeah, so I mean, okay, so the question will be what is actually happening. If you have a supernova explosion, then the time scale between when did you get the gravitational wave signal and it breaks out of the star is just really what's the photospheric radius of the star and what's the velocity of that expanding material, right? So you can, unfortunately, there's uncertainties in all of that, but if you look at the data, you know, they're happening everywhere from there's examples. 2008D is an example where it was very quick, and so within 1,000 seconds you had an X-ray signal. There was an Einstein probe detection this year where they got on it at the few thousand to 10,000 seconds. So it's unfortunately it's at that level of uncertainty. We have Einstein probe that could get us some X-rays now. The Chinese instrument. These are things where that we probably need some more coordination there to make sure if you see something, how quickly can you get, I think we'll have to be lucky with Einstein probe where it just happens that Einstein probe is putting in the same direction as the event as well. Yeah, I mean, you had a broad question, so that's a specific answer just for the X-rays.
Yeah, and Mikhail, you'll also see if UVX launches and ultrasat launches, you'll see as a counterpart to Einstein probe, within the first days, you can capture shock breakout. And you've seen for A7A early, within the first 2 weeks, evidence of gamma ray emission, X-ray emission from mixed metal eject out into the outer envelope. So there are countless ways to probe in ENM the rich features of breakout.
Coming back to what was said earlier, I mean, if there is a collapse to a black hole and that black hole will be wrong, we have a lot of experience in finding ringing black holes, right? And there's a very clear distinctive signature between Schwarzschild Kerr and Nordstrom Kerr and beyond GR Kerr and whatever, right? Because that is a very clean signal. And I do think one of the ways in which, maybe to find a failed supernova is to look for the forming black hole, right? And that's something that we know how to do. We know how to do very well. And it's very precise because the ringing is really only depending on one or two parameters. So I think it's worthwhile to think about these things and to really put all the pieces of the puzzle together, not just look at the supernova signal, think of the black hole signal, think of the proto-neutron star signal, and really put all these pieces together, because I do think that otherwise there can be a lot of confusion, right? As we don't know whether it's just other stuff going into a neutron star, etc. So, yeah.
Yeah, yeah. Olivia, I wanted to just finish answering your question Basically, whether you have spherical collapse to a Schwarzschild black hole or axisymmetric collapse to a Kerr black hole or three-dimensional collapse to, and we don't have an analytic solution in that case, the singularity structure changes, right? The Schwarzschild black hole, you have a single horizon. The Kerr black hole has a more complex horizon structure, has, multiple horizons and a ring singularity, as you said, rather than a point singularity. But the point is that in the numerical relativity community has developed the capabilities to, you take space-time, you slice it in space-like hypersurfaces, constant T slices, and you proceed forward. And that's, of course, the formulation we need in numerical simulations. And essentially, regardless of whether you have a point singularity or ring singularity, the main thing is to stay away from it, because if you touch it, whatever the case may be, things will become infinite. So you don't get saved if you have a Kerr hole versus a Schwarzschild hole. And of course, in 3D, we don't have a good understanding, a similar understanding of the horizon singularity structures. The point is, though, we do have an understanding, as Johnny was saying, of how to evolve space-time, so to keep the slices away from those problem regions. And of course, there are different slicings, some smarter than others. Different slicings are used for different cases, and some have their advantages and disadvantages theoretically and computationally. But basically, that's the point, if that makes sense. Yeah.
No more hands up. Ooh.
So, like, based on the templates, similar templates, how confident we are about like the core collapse will evolve into black hole or non-black hole? How confident it's? Sorry.
Yeah, that's a great question. I'm happy. Obviously, I'm foaming at the mouth to answer that. No, actually, there's two things here, right? I think we're seeing the emergence of, even Fulvio Ricci said this to me back in Pasadena when the communities were together, and he saw relative to 2010 in the meeting he held at Sapienza, and he saw the progress that the community had made in 7 years, and he was seeing these spectrograms, with the high frequency feature and the low frequency feature and the memory and and all that. So I think with regard to that, I think, I would say, at this point that part of the signal, seems to be robust, and we understand our understanding of it is pretty significant. I think earlier than that, as I'll discuss on Friday, I don't think we know very much at all, except maybe for the bound signature. So I think that particular signature will be there both for successful and failed supernovae, for neutron star or black hole formation. Some portion of that will be there. Where the cutoff is to black hole formation versus neutron star formation, that we don't know. We cannot answer confidently. The models are just not at that point. It's going to be a while before the models get to that point where we can really speak to that. And part of the problem is that even if we do our job within our sector of the problem, right, and advance the, neutrino radiation magnetohydrodynamic simulations in full GR, right, all the microphysics and the progenitors, right, there'll be the uncertainty in the progenitors, right, et cetera. There'll be other uncertainties. I'll discuss some of that. So it's going to be a while before I think we are confident in making that determination. But that doesn't mean we shouldn't try from now. We obviously, people in the community, Evan O'Connor and others have worked on this, and we have to make some statements about this going forward. You don't walk away from a hard problem, you just chip away at it, right?
We have one more follow-up.
And just to offer my own 2 cents, how confident are we that these form black holes? I would say not at all. because there's the very real possibility of having late time fallback where you don't have just infalling material in the first seconds triggering collapse to a black hole. If you can just continue these models out to hours, to days with some approximations, you can see sustained fallback of material because you blow up a star that's 15 solar masses. In the first seconds, you only explore the innermost core, which is 4 or 5 solar masses out to carbon and oxygen. So you have this entire hydrogen envelope with some metals out there that you have yet to unbind, and the explosion is very asymmetric. That's sustained asymmetries. And so you have explosion along some directions, funneling matter in along other directions. So it's very possible to have seconds to hour duration fallback that can then trigger formation of a black hole at later times, even with a robust explosion.
That's right. Yeah. But the question was, are we confident in, given the progenitor mass, not that we are certain about progenitor masses, we know what the error bars are there, but given the progenitor mass, how confident are we to determine whether or not it will become a black hole or a neutron star?
Yes.
That's the question. You're describing scenarios in which black holes can form. So David is right. We can form black holes in these. We can get explosion and form black holes too. So we can have our cake and eat it too, right? But to your question, where that line is, we don't know. And if anybody tells you they know, they're lying.
Yeah, that's absolutely right. And like we were familiar with these like 2018, 2016 maps where it's like Jackson Pollock painting an astrophysics picture where it's just barcodes. This star explodes, this forms a black hole. But that's not determined in the first seconds. So we are even further from determining what the reality is than we think we are.
But we're doing it. We're getting there. We got to be careful here. We don't want them to lose faith in us.
So I think there's a lot of discussion about these very specific things, but I think the models are simply not there yet. And I mean, there's been examples of things that we can do and different scenarios we can distinguish between. And I'm pretty sure that I can come up with counterexample to every single thing that has been said here. Like, and this is really true. Like, and to take one concrete example, you said that one way to tell that a black hole has formed is that we can look at the memory, and then when the black hole forms, the neutrino emission goes away, and then the memory doesn't grow anymore. But what if the memory is saturated before the black hole forms? So that's a counterexample to this one specifically. And we can probably go through the list and come up with counterexamples all the time. So I feel like we should be careful and not be too greedy with what we can detect and what we can do, but continue to develop the models. And I think we shouldn't make these very strong statements at this point. I think it's very dangerous.
But remember, I think I don't disagree with you, Hawken. But let's take your counterexample about the memory. Now, remember, it's not just the memory there. There's the high frequency feature there. So if you want to tell me a scenario where all of a sudden, the high frequency feature changes from being, say, sustained Ledoux convection induced to, as Johnny pointed out, some ring down feature of the black hole that's formed, and the memory, has saturated before, you know what I mean? There'll be multiple signatures, not just one. So anyway, but I guess I don't agree with you, but.
I will try kind of to steer us to the detection path. And I have two questions to people who is working in theory. The first question is, how many simulations you can really produce? 1, 10, 100,000 with different boundary conditions.
Models are valuable, but they're not all created equal. What we would call first principles models now, even with their Frankenstein nature in certain respects, it's the best we can do now. Very few. Now, if we're producing many, then we're making approximations, and there's nothing wrong with that. You have to have both. You have to have, large number of simulations that are more landscape studies, but we should remember that, the few simulations that are produced that may not run as long or may not be as many are really the fiducial simulations against which everything needs to be compared and referenced going forward. Now, those simulations will improve as our you know, as applied mathematics methodologies improve, as the our ability to muster all you know, heterogeneous computing, leadership computing platforms improves, as the platforms themselves improve, we'll be able to run more models and run them longer. But that is a slog. That is a decadal and beyond decadal effort. And that's there has to be this fiducial, this banister to which on which we hold and balance, and then everything else comes into play. Yeah, so very few in a year, very few.
I don't want to limit anybody's, you know, kind of creativity. And of course, people should create whatever model they like to create. But I hear on this meeting, I hear words. We all kind of agree on this. Does it mean that we can isolate some sort of a baseline model or baseline view, which will limit, you know, some class of potential morphologies of the signal? Is it possible, or it's totally crazy idea?
As the specification of that becomes more detailed, then it will run into disagreement. But I think the answer is yes. I think we've seen it. So first of all, I think it's been demonstrated across groups, across progenitors, you know, with models that are very sophisticated, albeit not what we finally will need, that neutrino-driven explosions, you know, are possible, and in many of the models generate explosion energies, et cetera, that are commensurate with observations, the trends, right? So that's already a starting point just from the pure theory side. Now, you know, you've seen from the gravitational wave spectrograms, that's the best, because there visually you can see the canonical features. And I think everyone here would agree. I would be very surprised that, you know, we have this high frequency feature, we have a low frequency feature. This is particularly at later times post bounce, at post 100 plus milliseconds. I think these are features that you were asking me about during break as well, that I think are canonical in the sense that we all see them. There are some variations. Maybe somebody doesn't have as much of evidence of SASE at low frequency, but the high frequency feature is always there. In explosion models, the memory is always there. The memory ramp up, I should say, is always there. And generally, there is SASE, neutrino-driven convection activity in all the spectrograms as well. Just it varies as to the strength and the periodicity, et cetera. But that's canonical, right? That supernova spectrogram, it took us a long time to you know, the community to get to that point, to be able to confidently speak to that.
Yes. So there's we can never simulate every star, right? So and predict the gravitational waves for all of them. So I think the goal has always been to understand enough that we can make some model to predict the gravitational waves for the ones that we can't simulate. And there's lots of people who already doing work in that direction, like the people at Valencia have their universal modes and phenomenological models, and I've done some stuff with Bilby.
I kind of have this feeling that like people who is doing data analysis, they like to detect detectable. You know, if you see some signal like out to 10 megaparsec, it's great. But I think that there is a danger that we can actually not be ready for realistic. And this may fall kind of through the cracks. You know, and kind of focusing and clearly identifying, you know, what could be realistic models, and you know, are we really interested to detect this? Then it would be a clear message to people who is doing data analysis.
If I can
Because detecting sine Gaussians is exciting, but not very useful.
If I can say one thought is that, I know, if we go back to the history of the field, people said, okay, we understand binary systems well enough that we want to have a search that is very well dedicated for that. And then we're going to do the burst group just in case there are unexpected things. But this part where we have strong theoretical reasons to have this morphology, we put real resources for that. Maybe we are going in that direction with the supernovae in the sense that there are some morphologies that are sufficiently motivated that we should do something focused for that, and then do the next generation of burst group for the rest. I don't know. That's a thought.
Is there any young people that would like to ask a question?
I have a naive question on failed supernova gravitational wave detection. So if an EM candidate for a failed supernova, such as infrared transient, is detected, is it possible to search for gravitational wave detection at that time and investigate what is happening in the failed supernova?
Anyone want to answer that? It's basically yes, but someone can fill you in with the details.
Too many details. I just want to, I mean, essentially, if I've understood correctly, you know, we have an electromagnetic signal, you know, as Pablo indicated, you know, if it's galactic, we'll have the neutrinos. And so game's on, right? I think we're good, but maybe you were thinking of something more detailed, did I understand the question?
EM transient, so can we get inner information as, for example, timing? Yeah. So if we get a shock breakout time, so before a few days ago, the gravity wave signal was ejected, and if we search in that days as a signal, so can we get the inner information such as a black hole spin or mass, or whether there is Sashi or convection or other information? This is my question.
So I think the first problem is going to be, where do you look? Well, if the signal's really loud, then maybe we would have just saw it already. But if you want to do, if the signal's really faint and we need to do a really like deep search for the gravitational wave signal, then the time window is going to be like from the time when you found out the star disappeared to the last time it was observed. So that could potentially be a huge window. So you're going to have that problem. So you might not have any benefits over like a all sky regular unknown burst search if your time window is where the gravitational wave emission was huge. But if we did see the gravitational wave signal, then we should see the SASI if it's nice and loud, and we should still see the high frequency dominant mode, at least until the black hole occurs. And then and we should see a neutrino signal, which would also show signs of SASI, and hopefully the black hole formation as well. So if you have a disappearing red supergiant, you should get a whole wealth of information still in gravitational waves and neutrinos. Okay, Marek wants to ask something.
So tomorrow I have my presentation, and I have a lot of questions and requests to the modelers, but it's coming tomorrow. But I have a question. If we have a detected gravitational wave, how quickly would it be useful for you to get like information of how it looks? I know it's like you will get, for example, peak frequency like automatically if you have a detector, say 700 hertz or 300 hertz, and then you'll be waiting until, say, we publish the paper. But how would it impact actually your simulation analysis for that specific galactic supernova?
Maybe I'll ask the question differently. Like if we send out a low latency alert for a supernova and we have like the peak frequency and the, I don't know, the signal to noise ratio, will you be able to learn something interesting about that and scoop all of our nice astrophysical statements about the event?
Jade, I think you're, and Marek, I think you're bringing up the most difficult question of all, because I've had this conversation yesterday with Thomas. What would happen if we really had this lucky instance of a supernova gravitational wave detection? And being an empiricist, I look back at what happened when GW 170817 was detected, and I think there was some triumphs, and some of the theory community and observational community reacted very well and adeptly to that. But I think there was also a big avalanche of other papers. I think if the ideal thing that I could imagine is that we actually manage, or a few of us actually manage, as soon as possible, using that data to come up with something which is maybe something of a consensus statement, maybe something which is reliable relatively quickly, despite all the discussions that people are going to have about zillions of different interpretations. If we had that in place organizationally in the community, and if then you can get us some data quickly, I think that would be something that I certainly would be looking forward to, and maybe others in the community would see that as a positive as well. I don't know.
Other than that beautifully articulated and diplomatic response. So a galactic supernova, just as an example, is, to say the least, far bigger than any one of us. And it would be an absolute pity if we put our own self-interests ahead of such an event. The science that we would learn from that, what we would give humanity in return. It would be a pity in such an event if the LIGO, members of the LIGO scientific collaboration did not shoulder to shoulder collaborate with experts outside when such an event occurs, in order to extract the maximum amount of information to maximize the scientific interpretation and scientific information that we would get from that. If it didn't happen that way, it would be less significant. It would be much less, with all due respect to the members of the LIGO scientific collaboration, because this is a hot potato topic, right? This is a political thing. This is complete when it comes to, we are scientists, and we need to focus on the science first. That's why this meeting was created, for this very reason, to get away from this nonsense. Okay, so when this data becomes available to you guys, it needs to become available to us as well, because together we will create something, you know, far greater than we could create individually. And that I say that on both sides of this. What a shame it would be to publish and then to have the external experts, you know, criticize something that was said or interpreted. I mean, that we want to avoid that. Again, this is far greater than we are individually. Let's not be selfish about this. Let's not worry about scooping. This is too important. Okay, so this is how it needs to go down.
That might be what you would wish, but it's not what's going to happen. We'll write the paper. If you want to be on it, you've got to join the LBK. And then you get the data when the paper's published. That's exactly what will happen. That's the plan. That's what we do for every detection.
You know, yes. So let me, you know, I really shouldn't say this, but it would behoove the LBK to fold us in, right? It cuts both ways. Okay. It's not about it. We are all working very hard, right? There's been 60 years of modeling efforts to get us to this point. And without us, you'd be flying blind. Okay.
I would argue that we have lots of internal experts. Well, IGWN.
So first of all, the things need to be planned in advance. You cannot start thinking about these things after you have a detection. So you modelers, you should come up all together with a consortium or with some structure. Okay. In a way that the LVK or IGWN can write an MOU with you that spells out what will happen. First of all. Second of all, it's not that Betelgeuse explodes tonight. You get a low latency alert. But we saw this morning all the checks that need to be done on the data. So I don't think you want the data right away unless they are vetted and checked and so on. So you might need to wait. Right. Right. But these things need to be planned in advance, because if there is a detection, then you all have very good intentions, but you know, things will start happening not in a clear way, right?
And it's just lying dormant and can be brought to bear in precisely the way you suggest. I couldn't agree with you more. I'm not speaking to your points are very well taken. You know what I'm speaking to, right?
Tony, I've seen exactly this happening. What Jade mentioned in the case of the gamma ray bursts and not gamma ray bursts, the neutron star mergers. So there was inside and outside LIGO activity, and only the inside LIGO activity got access and information of the data, not the outside. So this is not a unique situation, and I mean, either you join or you are out. I'm out, but anyway, for good reasons. But I mean, before we actually talk about the yields, maybe we should actually make sure that the measurement really can take place. And there's an interesting question which Tobias and also Marek and myself had already discussed. I mean, what's the chance actually? The question is very specific, what will happen after 05? And the question generalized means, for the next 1 or 2 decades, will we have gravitational wave detectors on all the time? Or is there a fair chance that they have maintenance or no funding or no interest, or they wait for the next generation to come up? and don't want to continue putting money into the existing one. So what is the perspectives to have full-time coverage? And even then, we may not, as Marek also told us over lunch, may not have the 100% chance to detect the supernova if the position is not favorable. So, I mean, we talk about what we say in German, ungelegte Eier. So the eggs are not yet out, and we already talk about them. Let's talk about the perspectives to really get a signal, and then we can see who gets the most yield of that.
So I looked at that question about after 05 and I thought, oh no, because now if you look at our observing scenarios, they've actually grayed out 05 because they're not even sure whether there'll be money for that or not. So on that note, I'm going to end the session. Let's go. Thank you everyone for the discussion, and I'll see you tomorrow. And I will keep this, and you can reply to questions and things whenever you like.